Hello and welcome to A Level Math. Today's topic is sets. So, you might have heard the word set in a general context, like set of some things, like a set of a bunch of apples, or a set of some some pencils, or anything. So, let's start with the very definition of sets. A set is a collection of well defined objects. So, what do I mean when I say well defined objects? When I say well defined, I mean that the elements inside the set should not differ from person to person. Say, for example, if I say, if I say a bunch of apples, then an apple is an apple either for you or for your friend. But if I say a set of some difficult problems in your maths book, then this is not well defined, because something that is difficult for you might not be difficult for somebody else. So, this is the meaning of well defined objects. A well defined object has to have the same definition for all the persons. So, let's take this example. The collection of all vowels in the English alphabet contains five elements. So these are the five vowels. So it is actually a set of all the vowels in the English alphabet, because vowels are vowels, be it you, be it your friend, be it anybody else. Vowels are vowels for everyone. So this collection is a collection of well defined objects. But if I say a collection of five most talented writers of India, then it might not be a set, because, and of course it's not a set, because someone who is talented for you might not be talented for somebody else. I mean, a writer whom you like might not be liked by somebody else. So that is the difference between a collection and a set. A collection can be a collection of anything, but a set has to be a collection of well defined objects. Well defined objects has to have the same definition for all the persons. So now let's take a look at the various methods of writing down the sets. So these are the various methods of set representations. The first method that comes is the roster form or tabulation method. In this method, we just list down all the elements of the set inside curly brackets. So let's take an example. A set of all the factors of 24. So we write down all the factors of 24 inside curly braces. So let's start with 1, then 2 is a factor, then 3 is a factor, then 4 is a factor, 5 is not a factor, then 6, 8, 12 and 24. So this is the set of all the factors of 24. Again, this is your discretion whether you want to include 1 and 24 or not, because they are the trivial factors of any number. So 1 is a factor of every number, and the number itself is a factor of itself. So 1 and 24, that's your discretion whether you want to include it in the set or not. So let's take up another example. The set of all months having 30 days. So can you give it a try? What are the months that have 30 days in them? So let's start with January has 31, February has either 28 or 29, March has 31. So we start with April, then May has 31, then June has 30 days, July, August, then September, then November. And these are the only 4 months, I guess, that have 30 days in them. So these two examples are the examples of sets. They are well defined. A set of all the factors of 24 has to be the same, excluding the case whether you want to include 1 and 24 or not, but still that's a set. So let's take up some questions. So what we are asked to here is that we are given some sets and we are asked to list down all the elements inside the set. So effectively we are to write down these sets in their roster form. Currently they are given in set builder form. We'll be studying about them shortly. So these are given in set builder form and we need to write them in roster form. So let's start with question number one. I won't be doing all the questions. I'll keep some questions for you as an exercise, as exercises. So let's start with question number one. So let's try and understand how to read this thing out. So A is a collection, or A is a set of all those x's where x is a natural number and x lies between 30 and 36, 30 included and 36 not included. So our set should look something like this. We have to start with 30 and go till 35 because it is set of all the natural numbers that start with 30 and go up till 35. 36 is not included. You know these two signs, less than and less than or equal to. So less than or equal to includes the number, strictly less than doesn't include the number. So our set will look something like this: 30, 31, 32, 33, 34, and 35. So that's it. Question number two, I'll leave it to you as an exercise. We'll take up question number three now. So C is a set of all those x's where x is a two-digit number. So it is a two-digit number such that the sum of the digits is 9. So what are those two-digit numbers where the sum of the digits is 9? So we start with 18, then 27, then 36, 45, 54, and finally we have 90. So these are the elements of this set. Okay, easy so far. Let's take up question number E. I leave question number D to you as an exercise. Question number 5. E is the set of all those x's where x is a prime number which is a divisor of 42. So if you remember, you might have done something like this. You are given a number and you are asked to write down the prime factors of those numbers. This is effectively this is what that the question is actually asking. It is asking you to find out all those prime numbers which are a divisor of 42. That means it is actually asking you to find out the prime factors of the number 42. So the first number is 2, and then we have 3, and then we have 7. So these are the three numbers which belong to this set. So 2, 3, and 7. Okay. Question number 6 homework. Question number 7. G is the set of all those x's where x is a prime number and 80 less than x less than 100. That means x lies between 80 and 100, both exclusive. So we have to write down all those prime numbers between 80 and 100, both excluding. Of course, they're not prime number anyway, but you have to think about it a little bit. So the first number is 83, I guess. 81 is divisible by 3 and 9. 83 is a prime number. Then 85 is not. 87 is divisible by 3. 89, I guess, is a prime number. Then I guess 91. 93 is divisible by 3. 95. 97 is again a prime number. 99 is divisible by 11. So that's it. I think these are the four numbers which are prime and which belong to this set. They are between 80 and 100. Question number 8 homework. Question number 9. So the set of all those elements x where x is a real number. Remember, x is not a natural number over here. It belongs to the set of real numbers. It could be fraction, it could be a decimal, it could be anything. And x has to satisfy this equation as well. So let's first solve this equation. X squared plus x minus 12 is equal to 0. We can factorize it as x squared plus 4x minus 3x minus 12 is equal to 0. This is the famous midterm factorization example. X common x plus 4 minus 3 common x plus 4. And then finally our factors are x plus 4 and x minus 3. So x is either equal to minus 4 or x is equal to 3. So these are the two numbers which satisfy this equation, and of course they belong to real numbers. So our set will be -4 and 3. That's it. I leave question number 10 for you as an exercise. Now, another way of set representation is the set builder form. Here we have to go in exactly the opposite direction. So here you'll be given a list of elements or a set with all the elements listed out, and you will have to write it in the set builder form. So set builder form will be the form we just saw. So let's take up an example here. Write the set A equal to 1, 2, 3, 4, 5, 6, 7 in the set builder form. So the pattern you have to follow for writing any set in the set builder form is like this. So you define the set and then open a curly bracket. Then write down an x over here. It's not that you'll always have to write down x, but let's start with this. So the set of all those elements such that it firstly belongs to the set of natural numbers, but it cannot be the entire natural number. It has to be less than or equal to 7. So the format is you open the curly bracket and then write down x over here, and then you define what your x is. So the first definition is that x has to be a natural number. You cannot take any real number, you cannot take any integer. X has to be a real number because 1, 2, 3, 4, 5, 6, 7 are all natural numbers. But then also you don't have to take numbers after 7. So you have to restrict x to less than or equal to 7. So this is how you define your set in the set builder form. Let's take up another example. The set H, let's first observe the pattern. It is 1, 4, 9, 16, 25. So the pattern here is that these are the squares of natural numbers. So this is 1 square, this is 2 square, this is 3 square, this is 4 square, 5 square, 6 square, and so on. So this is going to infinity, is not ending, okay? So H is the set of all those x squared where x belongs to natural numbers, and that's it. We don't have to stop it. It is going on. So x is the set of all those x's squared where x are defined like this. So this is the method of writing down the set builder form. So it's not necessary that you always have to x here. It could be x squared, it could be 5 times x, it could be 7 times x. It has to just define what you want to what you want your set to be. Okay, we'll take up some more examples now so that it's even more clear to you. Write each of the sets given below in the set builder form. So let's start with question number 1. A is the set. So what is the pattern of this set? It says 1 by 4, 1 by 9, 1 by 16, 1 by 25, 1 by 36, 1 by 49. So this is again 2 square, 3 square, 4 square, 5 square, 6 square, and 7 square, and is not going till infinity. It is stopping somewhere, and this can be written as 1 square, so that the pattern remains the same throughout. 1 square, 2 square, 3 square, and so on. So we define our set like this. It is 1 upon x squared, and then you define where your x is coming from. X is coming from the set of natural numbers, but you don't have to take all the natural numbers. You have to stop at 7. So you take x belong to natural numbers, say any number that less than 7, say for example 1, you put it down over here. So 1 upon 1 square will be 1, 1 upon 2 square will be 1 by 4, 1 upon 3 square will be 1 by 9, and so on. So this is how we write it in the set builder form. Question number 2, I leave it to you as an exercise. Question number 3, the set C is 59, 53, 59, 61, 67, 71, 73, 79. So if you observe the pattern, these are all prime numbers between 50 and 80. Okay, so so we write down the set of all those x's where x is a prime number and x lies between 52 and 80. Okay, so this is how we write down this set in the set builder form. Now question number 4, I leave it to you as an exercise, and we take question number 5. So the set E 14, 21, 28, 35, 42, and all the way up to 98. So if you observe the pattern over here, the pattern is that these are all the multiples of 7. So this is 7 times 2, 7 times 3, 7 times 4, and this is 7 times 14. So we'll write our set as 7 times x's, where x belongs to natural numbers and x goes from 2 to 14, because if you put x equal to 2 it will give you 14, if you put 3 it will give you 21, and all the way if you put x equal to 14, so 2 less than or equal to x less than or equal to 14. When you put x is equal to 14, you'll be getting your final number 98. So this is how we define our set in the set builder form. Okay, some special types of sets. So now we'll be discussing some special types of sets. The first one is the empty set. In an empty set, there are no elements. So an element that is actually having no set is called as an empty set. So this set is represented as just a pair of opening and closing braces without anything inside. So this is actually an empty set. Or you can also represent it as phi. This is read as phi. Okay, I'll make it again. So this is called as an empty set. Remember that you should not be writing empty sets like this, because in this way it will be having this as an element of the set. Okay, so make sure that you don't do this mistake in your examination. This will mean that this set is actually not empty. It is having an element inside the set. The phi is an element inside the set. So either you write down just the opening and closing parenthesis, curly brackets, or you just write down phi, but don't do this mistake. Okay, the second kinds of set are singleton sets. Singleton sets are those sets which are only having a single element inside them. Like this was an example of a singleton set. So singleton sets are those sets that just have one single element inside them. So it could be like 1, it could be like 0, it could be like apple, it could be like cow, and anything. It just has one single element inside it. Finite sets are those sets which are countable and finite. Means if you start counting the number of elements inside the set, you will reach an end somewhere. So say for example, if you write 1, 2, 3, 4 and so on, then this is a finite set, because you can easily count these sets, the number of elements in the set, and you will surely reach the end somewhere. Finally, we have infinite sets. Infinite sets are those sets where you can keep on counting and counting, but you will never reach the end. So if you take for example the set of all the natural numbers 1, 2, 3, 4 and so on, this is an example of an infinite set. You can go on counting and counting, it will never stop. This list is never ending. So this set is actually called as countably infinite set. Countably infinite set. There are another kinds of sets which are even uncountably infinite. When I say uncountably infinite, I mean that say for example x belongs to all those real numbers that are between 0 and 1. So between 0 and 1, there are infinitely many numbers. There are 0.1, 0.33, 0.69, 0.8975, 0.2950. There are infinitely many numbers, and you cannot even think of counting them. They are not even countable, because for any two number that you can give me, say for example, if you give me zero point 0.3 and 0. Say 9, then I can give you millions and trillions of number between these two numbers. So there is if I say there are no numbers between 1 and 2, at least there are no integers between 1 and 2, then that means we can have a pattern for counting them, 1, 2, 3, and so on. But in here we can not even follow a pattern for counting them, so they are not even countable. So they are uncountably infinite. Of course, they are infinite because there are a hell lot of numbers, zillions and trillions of numbers, but you cannot even count them. So they are uncountably infinite. So this is the example of an uncountably infinite set. Both of these kinds of sets come under the category of infinite sets. Okay, some more examples of infinite sets. The set of all points on the arc of a circle is an infinite set. So if you take a circle, then all the points on this circle, the set of all these points will form an infinite set. There are millions and trillions of numbers on this set. Okay? See, there is no way you can count them. The set of all points on a line segment is an infinite set. In the same way, if you take a line, then the set of all the points on this line will form an infinite set. There will be uncountably infinite number of points on this line. The set of all circles passing through a given point is an infinite set. So you take up a point. Now tell me how many circles you can draw that pass from this point. So this is one circle. There could be one more circle. There could be one more circle. There could be one more circle, and you can just keep on drawing circles one after the other, and you will never stop. So this is also an infinite set. You can have as many circles as you want passing through a given point. And lastly, the set of all straight lines parallel to a given line. Say for example, x-axis. If you take the x-axis, there are infinitely many lines that are parallel to this x-axis. Infinitely many lines up, infinitely many lines down. So they are all the examples of infinite sets. Now comes the concept of equal and equivalent sets. So what are equal sets? Equal sets are, uh, say for example, if I take A as 1, 2 and 3, and if I take B as 6, 7 and 8, then A and B are said to be equivalent sets. Equivalent sets will just have the same number of elements inside them. They will not be having the same elements. They will just have the same number of elements inside them. So A here is having 3 elements, B is also having 3 elements. So they are just having the same number of elements. So they are known as equivalent sets. So these are not equal because 1, 2, 3 and 3, 6, 7, 8 are not the same numbers. For these two sets to be the same, we need to have exactly the same elements inside them, and then only these two sets will be equal. So if I say that C is one more set where C is equal to 1, 2 and 3, then A and C are equal sets. So this is the difference between equal and equivalent sets. So here I want to introduce one more concept to you, which is known as the cardinality of a set. So cardinality of a set is the number of elements present inside the set. So and this is denoted as n of the set. So n of a means the cardinality of a. So here a is having three elements, right? So cardinality of a is equal to 3. Similarly, cardinality of b and cardinality of set c both is equal to 3. So if a set is having say 100 elements, then its cardinality will be 100. Okay. So equivalent sets have the same cardinality. All right. Okay. So let's take up some examples. Which of the following sets are examples of null set? Okay, so null sets are nothing but empty sets. Empty sets have two more names. One is null set and another one is void set. So these are three names of an empty set. One is empty set itself, another one is the null set, and the third one is the void set. So you have to tell me which of these is a null set. The set of all odd natural numbers which are divisible by 2. Okay, pause the video for a second and think about all those numbers that are odd and that are divisible by 2. Okay, so take some odd numbers, for example 3, 9, 11, 15, any odd number. Is any of these numbers divisible by 2? Of course not, right? Because if it had been divisible by 2, it would have been an even number, because that's the very definition of an even number. An even number is a number that is divisible by 2. So there is no such odd number that is divisible by 2. So this is actually a void set or an empty set. This is an empty set. Now think of this, question number 2. Set of all even prime numbers. So tell me some prime numbers that are even. It's 2 only, right? Because 2 is the only even prime number. All the numbers are divisible by 2. So 2 is the smallest prime number as well as the only even prime number. So this is actually a singleton set. This is not an empty set. It is actually a singleton set. Question number 2. Okay. Let's move ahead with some more examples. You have to still tell me which of these sets are null sets or if they are singleton sets. So question number 3, I'll do it for you. Question number 4 will be an exercise. So A is a set of all those natural numbers where this x lies between 1 and 2, 2 included but 1 not included. So this is actually a singleton set 2, right? Because one cannot be included and it has to be natural number. So the only number that is left is 2. Because natural numbers are 1, 2, 3 and so on. It says that it has to be between 1 and 2. 1 cannot be included. So the only option is 2. And it has to be less than 2. So the right hand side part of it is excluded. So this is a singleton set. Question number 4, I leave it to you as an exercise. Question number 5. C is a set of all those prime numbers that lie between 90 and 96. So tell me all those prime numbers that are between 90 and 96. So you start with 91, 93 is not, 90, 97 and 99 is not a prime. Okay, we have to just write down 90 less than 96. So 97 is not included. So this is again a singleton set. 91 is the only prime number between 91 and 96. Question number 6, homework. Question number 7. E is a set of all those x's where x belongs to the set of whole numbers. So x belongs to the set of whole numbers and x has to satisfy this inequality. So let's first simplify this inequality. X plus 3 less than or equal to 3 means x less than or equal to 3 minus 3, which is 0. So x is less than or equal to 0. So this is the simplified version of this inequality. So x has to satisfy this inequality as well, and x has to belong to a whole number as well. whole numbers are 0, 1, 2, and so on. So x has to be less than 0 only, so this side, and x has to belong to this set as well. So 0 is the only such number, right? So this is 0, again a singleton set. Okay, now question number 8 is in homework. Question number 9, I'll do it for you. This is of course a singleton set. It contains the single element 0. They're just trying to befool you. You will think that okay, it contains 0, so it contains nothing, but this is not the case. 0 is an element of this set. So this is not an empty set, but it is actually a singleton set. Which of the following are pairs of equal sets? So, question number 1, I'll try with you. So, what is this set actually? It is the set of all the letters in this word alloy. So, the set looks something like this: A, L, O, Y. Remember, repetition is not allowed inside a set. So, we'll not be writing L twice, it will just be written single time. So, this is how the set A looks like. Now, let's see how does the set B look like. L, O, Y, and A. We will not repeat L once again. So, and also remember that the order inside a set is not important. So verify whether these two sets are having the same elements or not. So A is here, A is here, L is here, L is here, O is here, O is here, and Y is here, and Y is here. So these two sets are actually equal sets. Now question number 2, I leave it to you as an exercise. Question number 3 we'll do. So E is the set of all those x's where x belongs to integers and x square is less than or equal to 4. So think about this inequality: x square is less than or equal to 4. So x square less than or equal to 4 means tell me all those numbers which on square give you either 4 or something less than 4. So what are the elements inside it? First element is 0, because 0 on being squared gives you 0, which is of course less than 4. Then you'll be having 1, because 1 squared is less than 4. You'll be always also having minus 1, because minus 1 squared is 1, which is also less than 4. And you'll be having 2, because 2 squared is 4. So that is a possibility. It can be 4 or it can be less than 4. And finally minus 2. So these are the 5 elements inside this set. So x belongs to integers, so we can take all of these sets because all of these are integers, and all of these numbers satisfy this inequality as well. So they have to satisfy both of these things. So that is why all of these 5 numbers are admissible. So this is how the set E looks like. Now let's see how is the F looking like. So F is the set of all those numbers that are integers and x square is equal to 4. So there are only two possibilities, 2 and minus 2, right? Because these are the only two numbers which on being square give you 4, exactly 4. It's not saying less than 4 or greater than 4. They have to be exactly 4. So these are the only two possibilities. So E and F are not equal sets. Okay, question number 4, I leave it to you. Question number 5. J is 2 comma 3. It's already written in roster form, so we need not bother about it. Let's write down K in roster form. So K is a set of all those x's where x is an integer and it satisfies this equality. Equality. So let's first solve this equality. So x square plus 3x plus 2x plus 6 is equal to 0. X plus 3 times x plus 2. So I'm doing a bit of step jump over here. I know you can do it. So the two values of x are x equal to minus 3 and x equal to minus 2. So these are the two values of x that satisfy this equality. And also they belong to the set of integers. So both of these numbers we can take. So k is actually -3 and -2. So you see 2 comma 3 and -2 -3, they are not equal sets. Had they been 2 and 3, they would have been equal. Okay. Okay. State whether the given set is finite set or infinite set. So let's take up question number 1. We'll be doing all these examples now because they are just either yes or a no. So we'll do it together. You try it along with me, okay? So question number 1, the set of all triangles in a plane. So consider your mobile phone screen or laptop screen in whatever device you're watching it on. So how many triangles you think you can draw on your screen? So this is one triangle, two triangle, three, four, and you can just go on drawing triangles. They can overlap. It's not saying that they cannot overlap. So overlappings are allowed. So you can draw actually infinitely many triangles on this screen. So this will be an infinite set. For now, I'll be writing I for infinite set and F for finite set. So to save time. So question number 2, set of all points on the circumference of a circle. This we have already discussed, right? The set of all the points on the circle is an infinite set. Question number 3, set of all lines parallel to the y-axis. We have also gone through this. Y-axis, this is suppose the y-axis. There are infinitely many lines that are parallel to the y-axis, right? So this is also an infinite set. Question number 4, the set of all leaves on a tree. This is a finite set because there are finitely many leaves on a tree. So you can take all the leaves out and then start counting. Maybe you will take a month or so to count them all yourself alone, but you can still reach the end someday. It is expected. So I think that's a finite set. Question number is set of all positive integers greater than 500. So what are the numbers that are greater than 500? 501, 502 and so on, and you can go on and on. There is nobody stopping you. You have to take all the positive integers that are greater than 500. So greater than 500 is 501, 502, 9000, 9001, 10,063, 1,77,895, and any number that is greater than 500 as an integer will be belonging to this set. So this set is actually an infinite set. Can you tell me whether it is countably infinite or uncountably infinite? Yes, it is countably infinite because you can go on counting 501, 502, 503 and so on. So this is countable, but it is infinite. Now question number 6. F is the set of all real numbers which lie between 0 and 1. So we have already discussed this is uncountably infinite set because there are zillions and trillions of numbers. There will be no pattern in which you can count them. You just can find millions and zillions of numbers between any two numbers that I give you. Say for example, if I give you 0.1 and 0.3, I can give you zillions of numbers between these two: 0.15, 0.19, 0.2395, 0.1589, 0.1234, or anything. There are infinitely many numbers between 0 and 1, and they are also uncountable. There is no pattern in which you can count them. So they are uncountably infinite. Question number 7. Set of all integers that are less than 1. So that's, I guess, the singleton 0, right? So this is actually a singleton set and it's a finite set. Question number 8. The set of all those x's where x belongs to integers and -15 less than x less than 15. That means our elements will be like this: -14, -13, all the way up to 14. Remember, -15 and 15 are not included. Had they been included, we would be having less than or equal to sign over here, but they don't have to be included. So it's just from -14 to 14, and it is clearly a finite set. Question number 9, 10 and 11 is the homework for you. I'm sorry, I'm a bit bored with this. It's quite easy. You just try it on your own. And finally, a recap of whatever we have discussed so far. So at the very beginning, we looked at the definition of a set. A set is a collection of well-defined objects. When I say well-defined, that means the objects should not be different for one person to another. So the definition of the object should be same for every person. Then we moved on to the methods of set representation. We discussed about the roster method, where we list out all the elements of the set, and then we discussed the set builder method, where we write down the set in inside curly brackets, where we define the properties of those elements. So we write down something like x, and then we define the properties of the x. Then the types of sets, they are singleton sets, empty sets, finite sets, infinite sets, and finally the equality and equivalence of sets. So these are the things that we have covered. So thanks a lot for now. We'll cover a lot more about sets. We are left with subsets and all those stuffs. We'll be dealing with them in the upcoming lessons. Thank you for your patience. Keep enjoying our videos. And till then, study hard, study smart. Bye bye.